Hi students, today we're going to continue looking at transformations of functions, focusing this time on stretching and shrinking. Let's take a look at a couple of graphs and compare them. Let's graph f of x equals the absolute value of x and g of x equals 2 times the absolute value of x, and we'll graph these on the same plane. Now we have already graphed the absolute value function, but since we haven't done it in a little bit, let's do it again. -3, -2, -1, 0, 1, 2, and 3. F takes the absolute value of x, so the absolute value of -3 is +3, the absolute value of -2 is +2, and then we've got +1, 0, 1, 2, and 3. So that's our table of values for f of x. Now let's make a table of values for g of x. What g of x does is it takes the absolute value of x and then multiplies by 2. So I'm going to pick the same x values, and then let's plug these into g of x. When we plug in -3, the absolute value of -3 is +3, and 2 times 3 is 6. Then, when we plug in -2, the absolute value of -2 is +2, and 2 times 2 is 4. When we plug in -1, the absolute value of -1 is 1, and 2 times 1 is 2. And so on. We end up getting 0, 2, 4, and 6 for the other corresponding function values. Now let's plot both of these on the xy plane and look to see what has happened. So for f of x, we've got -3, 3, -2, 2, -1, 1, 0, 0, 1, 1, 2, 2, and 3, 3. And we remember that this graph is a V shape with a 90-degree angle. Now for g of x, we've got some new points, -3, 6, -2, 4, -1, 2, 0, 0, 1, 2, 2, 4, and 3, 6. Here we have another V shape, but this one doesn't have a 90-degree angle. Something has happened to it. And what I want to do is I want to look at corresponding points here. We can see we've got the same x values in each, but the y values are twice as much on g of x as they are with f of x. So effectively what's happened is each of these points has moved twice as far away from the x-axis as it was before. And so what we're doing here is we are stretching things vertically. We're taking the points and we're moving them twice as far above as they would have been before. And if we had done something similar down below, any point that would have been below the x-axis would have also been stretched twice as far down there. So this is a vertical stretch of factor 2. So we are stretching things vertically with a factor of 2. Let me write that down. We have a vertical stretch of factor 2, or by a factor of 2. And so what I'm going to do now is I'm going to give you the rule here, and then we'll use the rule to look at another example. To sketch the graph of y equals c times f of x, if c is larger than 1, stretch the graph of y equals f of x vertically by a factor of c, which is what we had here. we had a c value of 2, a coefficient of 2, and so we stretched the function by a factor of 2. Now, if c is between 0 and 1, we shrink the graph vertically by a factor of c, and that's what we're going to do when we look at h of x. Here we're going to have h of x equals 1/2 times the absolute value of x. In this case, we've got something in the form y equals some number times f of x, and because that number is between 0 and 1, because it's less than 1, we actually shrink the graph vertically. So for each point on the original graph, it needs to shrink by a factor of 1/2. So the distance between that point and the x-axis is going to shrink by a factor of 1/2. So this point, instead of having a y value or a height of 3, will have a y value or a height of 1.5. We're cutting things in half. This next point, it's 2 units above the x-axis. When we cut that in half, it'll be 1 unit above the x-axis. The next point is 1 unit above the x-axis. When we shrink that by 1/2, it's going to be 0 units above. And this right-hand side is going to end up looking like this. It's shorter. And the same thing is going to happen on the left-hand side. Each point is going to be 1/2 as far away from the x-axis as the original point. And so this is our graph of h of x equals 1/2 times the absolute value of x. I want to show you one more example of what something might look like if we shrink it, because this example, we only have points above the x-axis, and I'd like you to see a situation where we also have points below the x-axis, and we are shrinking something. So what I'm going to do, this is not actually a function, but I want to give you a graph and show you what happens when we shrink it. So here I want to look at a circle that has its center on the x-axis. If we were to take this and we were to shrink it vertically by a factor of 1/2, then the top point would be there, the bottom point would move up there, and the side points would stay where they are. So what would effectively happen is we would end up, instead of with a circle, we would end up with more of an oval shape because it's not quite as tall as it was before. Everything kind of condensed, getting closer and closer to the x-axis. Hopefully, the examples in this video have helped you to see what it means to do a vertical stretch or a vertical shrink. In the next video, we'll look at horizontal stretches and shrinks to get more practice with stretches and shrinks.